Hey guys, this is Mrs. Razak, and this is our lesson on uh, lenses or Bray diagrams for convex and concave lenses. You can find the material for this section of our electromagnetic wave unit on pages 122, 123, 124, and 125. So the diagram you see on the screen illustrates a convex lens, and convex describes the shape of the lens, and it's the shape of the lens that determines how light will bend as it moves through the medium. You can see here that on the left side of the lens, we have two light rays that are parallel to the principal axis. So this dotted line that runs straight through the lens is known as the principal axis. These red light rays begin parallel to the principal axis. So we're going to call those parallel rays. When they reach the lens, they actually get refracted twice. Once when they enter, and again when they exit the glass. And it be due to the shape of the lens and where the light is incident, it causes the light to be bent so that this top parallel ray changes direction toward the principal axis, and the bottom parallel ray changes direction toward the principal axis but up. Where these two light rays intersect is known as the focal point of the lens. The focal point of the lens can be measured from the plane of the lens. That's a reference point. It's a vertical line running directly through the center of the lens. So from the plane of the lens to the focal point is known as the focal length. So here, a little bit of vocabulary. The focal point is the location at which light rays parallel to the principal axis converge from a convex lens. The focal length will always be positive for convex lenses, and it is on the side of the lens opposite the object. So the focal point here on the if your object is over here, which is where these light rays are coming from, the focal point will be on the opposite side of the lens from the object for a convex lens. And then this focal length will be a positive value. So these are known as sign conventions. So you'll need to keep track of some of these sign conventions. So focal length, distance from the focal point to the center of the lens, is a positive value for convex lenses. Just to give you a heads up, it will be a negative value for concave lenses, but we'll get to that in a moment. I already mentioned the principal axis is a line drawn through the center of the lens perpendicular to the plane of the lens. So here's an example of light refracting through a convex lens. So we have Mario on the left, that's our object. And we have two types of rays drawn here. This top ray here goes from the top of Mario's head parallel to the principal axis. That is the parallel ray. Once it reaches the lens, it refracts or bends so that it passes through the focal point. So these we would use a straight edge or a ruler to draw these rays. And at the top of page 122, there are detailed instructions of how to draw each type of ray, just in case you forget, but I will demonstrate that for you. This second ray begins at the top of the object, Mario's hat, and it's a straight line that passes directly through the center of that principal axis. So this point is the point where the principal axis crosses the plane of the lens. When you're actually drawing these, it can be difficult to get that to cross right where you want it to. But the closer you get to the kind of the crosshairs, right where the plane of the lens meets the principal axis, the more accurate your diagram will be, and you will be calculating percent error. So I mentioned yesterday that real images are always formed where light rays actually cross. So we can see here that the the parallel ray and the central ray cross down here. Now, we see Mario inverted. So one way you can always remember how to draw your image is that the base of the object is on the principal axis. So the base of the image will also need to be on the principal axis. So Mario's feet on the principal axis and the object, Mario's feet will also need to be on the principal axis in the produced image. This produces an image that is inverted or upside down. Whenever we see an inverted image, we know that it's a real image. So real images are easy to spot because they should always be upside down and they form where light rays actually cross. Due to the distance of our object from the lens, we can also see that the image is enlarged. It's bigger than the object. So we need to be able to describe the image formed from a convex and concave lens. And in this case, we have a real image that is inverted and larger than the object. So it's enlarged. Real images will always be inverted and they will always be on the opposite side of the lens from the object. So sometimes we see virtual images that are formed for convex lenses. A virtual image will always appear right side up. So virtual images are formed where the light rays only appear to intersect. So in this case, we can see that the light comes from the object. This is our parallel ray, parallel to the principal axis, and passes through the focal point. But this light ray appears to come from some point back here. Likewise, for the central ray, light begins at the top of Mario's hat and passes through the center of the lens. And we can see that these two light rays are diverging, but this central ray appears to come from some point back here. So where those two light rays appear to come from or appear to diverge from is where our virtual image will be formed. So this virtual image is erect or upright, and it is larger than the object. So we would describe that image as virtual, upright, and enlarged. So these are some steps for drawing ray diagrams, and I wrote these out to try to give you a systematic way to draw your ray diagrams, and you will be practicing those. So the first step is to measure and label the focal point and 2 times the focal point on each side of the lens. Then you'll draw the object at the specified location. You will draw each of the 3 rays, the central ray, the parallel ray, and the focal ray. Again, at the top of page 122, there are detailed instructions on exactly how to draw each one of those rays, but I will practice those with you. Once you get your rays drawn, they should all converge at a single point. That is where your image will form. So images are formed where the light rays intersect for a real image or appear to intersect for a virtual image. So I'm going to go through each of the different rays. Probably the simplest ray to draw is the central ray because it begins at the top of the object. It passes directly through the lens where the plane of the lens crosses the principal axis. It can be difficult to get your ray to pass right through those crosshairs. So if you are a perfectionist or a little bit OCD, this could make you a little bit crazy. I know that if mine isn't exactly where I would like it to be, I just erase it and try again. And if it takes me more than 2 or 3 times, I usually just, hey, it's close enough. And the closer you are to actually meeting those crosshairs, the less error you will have in your diagram. However, there is an acceptable amount of error for these hand-drawn ray diagrams. So that is the central ray, and really probably the easiest to draw. The parallel ray begins at the top of the object, goes parallel to the principal axis until it reaches the plane of the lens. Then it converges through the focal point. So we're going to draw that line through the focal point until it meets the central ray. And where those 2 rays meet is where our image is formed. So again, since the base of the arrow for our object is on the principal axis, the base of the arrow for the image also must be on the principal axis, which is how we determine that it is inverted or upside down. There is a third type of ray, and this one's a little bit trickier to draw, and it is known as the focal ray, and that is drawn here in green. So the focal ray begins at the top of the object, and it passes through the focal point on the left side of the lens. So we know these rays converge to a parallel ray will converge to the focal point on the right side, but we use the focal on the left side to help us draw the focal ray. So we will draw a line from the tip of the object through the focal point, and it should end right at the plane of the lens. The light will refract from that point horizontal to the principal axis. So it really is kind of the inverse of the parallel ray. The parallel ray first starts off parallel and then converges through the focal point. The focal ray begins at the tip of the object, passes through the focal point, and after it's refracted on the convex lens, it continues parallel to the principal axis. Oftentimes, these 3 rays are very difficult to get to converge at the exact same point. Ideally, they should, but just because of our method of using rulers and pencils, it's oftentimes difficult to get all three to converge at the same point. And again, that is where our real image is formed, and we would describe this image as real, inverted, and smaller than the object. Earlier, we discussed object distance in terms of reflection from a flat mirror, a plane mirror. Object distance and image distance always also applies to lenses. And the basic definition doesn't change, but we will add some sign conventions. So, for example, here, the object distance is just the distance from the object to the lens. For lenses, the object distance is always positive. Okay, so object distance always positive. The image distance is the distance from the image to the lens. So notice this image is on the same side of the lens as the object, and it is upright. So this is a virtual image. It's formed on the same side as the object, but this image distance is considered negative. And again, this is a sign convention, and it basically makes the math work out correctly. So for the image we see here of the little Mario, the virtual image will have a negative image distance. If I go back to the previous slide, this image distance would be considered positive. So the image, when the image forms on the opposite side of the lens as the object, the image distance is positive. When the image forms on the same side of the lens as the object, the image distance is negative. And you will need to use these sign conventions once we start calculating with the lens equation. So before I move on to concave lenses, I would like to discuss, I thought I had it on here. There it is. The lens equation. So this inverse relationship says that 1 over the focal length has to equal 1 over the object distance plus 1 over the image distance. So if, for example, I knew the object distance and the image distance, I could solve for the focal length. However, I would need to make sure that I do my algebra correctly, because if I get a fraction of, 1/8 for 1 over DO plus 1 over DI, my focal length would be the inverse of that, which would be 8 over 1. And we will definitely practice that. And I'll get back to this. This is a chart that lists out all of our sign conventions for the different types of lenses. So this is page 122 and 123 in your workbook. And as I mentioned, there is just a reference chart in case you forget how each type of ray is drawn. And it gives us some instructions here. And so 3 light rays intersect on the right side of a lens to produce an image. If the 3 light rays do not converge, project the rays of light back through the lens to the point from which they appear to diverge from. If the 3 projected rays intersect on the left side of the lens, an image of the top of the object is located at that intersection. So the first step, which is, the first step here was the rules. So in drawing a ray diagram, the first thing we want to do is we want to label the object distance, image distance, label the image I, the object O, the focal length F, and 2 times the focal length, which is really a reference point. We're going to indicate where the lens is and the principal axis. So for our ray diagrams, which we will draw here on page 123, we will use a focal length. Since these are convex lenses, they will have focal length of 3 centimeters. So a clear ruler works a lot better for this application than a non-clear ruler. So it just makes your life a little bit easier to judge. So I need to label 3 and 6 centimeters on each side of the lens, and the lens is this vertical line. So I'm going to put my ruler right at 12, and then I can easily measure 1, 2, 3 centimeters. That's my focal. 1, 2, 3 centimeters. That's 2 times my focal. I'm going to do the same thing on the other side. The only problem here is that it doesn't look like it looks like I can just make 2F. So I'm going to label on both sides of the lens F and 2F. And now I can get started on my ray diagram. So up here next to the number, it tells me the object distance needs to be greater than 2F. So 2F is at 6 centimeters. So as long as I put my object at any distance from the lens greater than 6 centimeters, I have satisfied that condition. So I'm going to go ahead and measure 7 centimeters from the lens, and that's the point where I'm going to draw my 1 centimeter high object, because it tells us here the height of the object will be 1 centimeter. So at that point, I will measure a 1 centimeter arrow with the base of the arrow on the principal axis. That is my object, so I'm going to label it O. So I'm going to get you a little more definition here. All right. So now it's time to draw some rays. I typically draw the central ray first, but it really doesn't matter what order you draw them in. I draw this one first because it's straightforward because you know how to draw it, but it can be challenging to get it to pass directly through the where the principal axis crosses the plane of the lens. And if we look at this, I'm definitely over to the right just a little. So my OCD, this is why I draw it first, so that I don't have to erase other lines, but my OCD is not going to allow me to have that error. If I do it again and I still get some error, I'm just going to roll with it and hope that my error isn't greater than 10%. So I'm lining up my ruler with the top of my object, and I want it to pass right through where the lens, and that looks quite a bit better. Yeah, I'm off maybe just I'm off maybe just a hair, but I'm going to call that good enough. So there's my central ray. This is where the clear ruler really comes in handy because it allows you to see your principal axis so that you know that your parallel ray is actually parallel. So I'm going to draw a line parallel to the principal axis from the top of the object to the lens. And I can judge where my principal axis is by where it falls on these numbers here in the clear ruler. So that's going to go to the lens. A principal ray converges through the focal point. So I'm going to line up where that principal ray, where the parallel ray intersected with the plane of the lens, and I want that light ray to converge through the focal point. So I'm going to line it up with the focal point. And I see already that my light rays are converging right about here. I'll go ahead and draw that third ray, the focal ray, but oftentimes this one is the most difficult to get to cooperate and meet all in the same place. And it really depends on the error of the other rays. So there is the focal ray, which will then, I'm going to turn this upside down just to try to get a better idea of whether I am parallel or not. It looks. I'm going to go with it. So really, I did a pretty good job. I'm kind of happy with that. It doesn't usually come out that nice. I do have a little bit of fuzzy area here that I have to kind of guess where these three rays meet. I'm going to guess it's right about here. So I'm going to draw my image. At that point, the base of the arrow of my image needs to still be on the principal axis. So I see a inverted image that is obviously real because the light rays crossed, and it's inverted. So we can use our equation, 1 over f equals 1 over dO plus 1 over di, to determine the ideal image distance. So I'm going to label the object distance here. So from the object to the lens, I'm going to label, that's my DO, my object distance, and that was equal to 7 centimeters because I measured it. And then my image seems to have ended up at 5.3 centimeters from the lens. So I'm also going to label my image distance from the lens to the image. That is image distance, DI, and 5.3 centimeters. So this is my experimental value. So I know my object distance. I know my focal length. So I want to see how close did I come to this experimental value for where the image will form from this lens. So I'm going to rearrange this lens equation to solve for DI. So I'll have 1 over the focal minus 1 over DO equals 1 over di. My focal was 3 centimeters minus the object distance of 7 centimeters, and that is going to be equal to 1 over di. When I plug that into my calculator, 1/3 minus 1/7 gives me 0.19. But 0.19 is equal to 1 over the image distance. So the easiest way to take the inverse is to simply click on the inverse button, which looks like x to the negative 1 here, just below the math button. So if I click on that, it tells me that my accepted value for image distance, I'm just going to write this here, image distance, what I calculated is 5.25. My experimental is 5.3, so I was pretty close, but am I within 10%? So I'm just going to zoom out for a sec and show you where to find. Okay, so, I did not I described the image, but I didn't write it down. So I know this is a real image because light rays actually cross. It is inverted or upside down, and it is smaller than the object. So that is my description. Then I calculated the image distance using the lens equation. Now I'm going to calculate the percent error. My measured distance, or my experimental distance, is the 5.3, and my calculated is the 5.25. I suggest that you do these calculations on a separate sheet of paper because clearly they get, there's not enough room to really do them all in the same place. So I'm going to go ahead and say my measured value, 5.3, minus my experimental, my calculated 5.25, and I'm going to divide that by my calculated 5.25, and take that, multiply by 100. Whew. Not even 1%. Hey, that's pretty good. So my percent error, and I would like you to show your work, is 0.95%. So less than 1% error. So not too shabby. So that is generally how to draw ray diagrams. I want you to practice 2 and 3 on your own. The only difference here is where you're going to place your object. So in the first one here, I placed my object at a position greater than 2 times the focal length from the lens. Number 2, you're asked to place the object right at 2f. Number 3, you're going to put it somewhere here between f and 2f. I do recommend that you measure and place the distance at the distance of your object at a whole number value, or at least a round number value, so that you don't end up with some kind of funky decimal that you need to carry through your math. Number 4 is a little bit different, so I want to do that one with you. We're going to start off the exact same way. So we have a 3 centimeter focal length. So I'm going to place my ruler right here at 6 centimeters. And then it makes it really easy for me to mark F and 2F on both sides of the lens without moving my ruler. So this is F and 2F on the right, and F and 2F on the left, and those really are just reference points. And it tells us, oh boy, I drew it on the wrong one. I told you to do number 3. So number 4 I really don't have enough space to put 2f on the left, and there's a reason for that. But I can put f and 2f on the right and focal on the left. And then it tells us that we should place our object right at the focal length. So I'm going to draw a 1 centimeter high arrow right at the focal length, right at 3 centimeters from the lens. And I'm going to label that O for object. Here is my lens. I will start off with the central ray that I would like to pass directly through the crosshairs with that are the plane of the lens and the principal axis. And I'm pretty happy with that. I got pretty close. I'm a hair off again, but I'm going to call it good. Then I'm going to draw the parallel ray. And I'm just checking with my ruler to see that I'm crossing those numbers in about the same spot so that I know my parallel ray will indeed be parallel to the principal axis. And then this parallel ray should pass directly through the focal. So here is my focal ray. Now what you might notice here is that these two lines are parallel. Parallel lines will never cross, even if I back them up this way. They're parallel. They're never going to cross. So when the object is at the focal length, no image is formed for a convex lens. So that one's just a little bit different than the others. Likewise, number 5 is a bit different. So I'm going to mark F on the right side, and on the left side I actually am able to mark both F and 2F as my reference. So F and 2F. In this case, it asked me to place the object less than the focal length. So I'm going to place it between the focal point and the lens. It really doesn't matter where you place it, but I do recommend that you measure it. So I will place mine right at 2 centimeters. That would be 1 centimeter from the lens. So I'm going to draw a 1 centimeter high arrow 1 centimeter from the lens. And this is my object. I did not label my object distance over here, so I'm going to go ahead and do that. 3 centimeters. Okay, so I know my object distance is from the object to the lens, and I determined that to be 1 centimeter. The central ray goes from the tip of the object directly through the center of the lens where it crosses the principal axis. So I have a light ray that will go through that point. These two lines will not converge. So what I'm going to do is I'm going to draw a dotted line backward from the object to indicate where that light ray is coming from. I will then draw the parallel ray from the tip of the object to the plane of the lens. That light ray will converge through the focal point. And as you can see now, these two light rays are diverging. So again, I'm going to draw a dotted line back to some point where this light appears to be coming from. Where these two light rays appear to converge is where the virtual image is formed. So right about here, I have an image formed. It is upright. I know that because this is my image. I know that because the base of the arrow still needs to be this is the O, DI. Now this image distance is going to be negative. I can measure from that image to the plane of the lens, which is 1.75. So that's going to be negative 1.75, because when the image ends up on the same side of the lens as the object, we're going to call that a negative image distance. So I can again use the wave equation, 1 over f equals 1 over do plus 1 over di, to calculate the image distance. So 1 over the image distance equals 1 over f, 1 over f minus 1 over do. So 1 over the image distance equals 1 over 3 minus 1 over the object distance of 1. So 1/3 minus 1 would give me a negative 2/3. And since that's equal to 1 over the image distance is equal to the reciprocal of that. So negative 3/2 or negative 1.5. I got negative 1.75. So I think I might be in a situation where I'm more than 10% error. And it may have even been with my measurement. But I'll go ahead and calculate it using the equation provided on page 122. So my measured distance, negative 1.75, minus the calculated distance of negative 1.5. I'm going to divide that by the calculated distance of negative 1.5 times 100. Oof, 16.67. So I would like to see percent error less than 10%. So honestly, this one, I would start over. I would erase the whole thing and start over until I get an image distance. I'm going to remeasure. Maybe I didn't measure it correctly. Oh, well, that actually makes it worse. Yeah, I'm getting like 1.8 now. So I really just need to do the whole thing over again and check my measurements. So if you get a percent error greater than 10%, go ahead and just erase and start over. So it's real important that you do this in pencil. So you're just going to do 2 and 3. The ones that produce a virtual image are actually a lot more difficult because the difference between the measured and calculated distances are very small. So it's easy to get a high percentage of error. But I will go back and try again. So convex lenses are called converging lenses because light rays parallel to the principal axis converge to a single point. And focal length for convex lenses will always be positive. Object distances also always positive. Image distances are positive if they're on the opposite side of the lens from the object. Image distances on the same side of the lens as the object are considered negative, even though the object distance is still considered positive. So object distance is always positive. So there we have that. I'm going to just do one of the concave ray diagrams for you. Concave lenses are diverging lenses. And so if you look at this parallel ray, they're called diverging lenses because light rays that are parallel to the principal axis, when they refract through the lens, they diverge from a focal point on the opposite side of the lens. For that reason, focal lengths for concave lenses are always considered negative. So this focal length, I'm going to fill in here, we're going to have a negative focal length, -3 centimeters. The rays themselves are drawn similarly. The central ray is drawn exactly the same. The parallel ray, parallel to the principal axis, instead of converging to the focal point on the right, it diverges from the focal point on the left. So you'll need to draw that one a little differently. And then the trickiest one to draw is the focal ray for the concave lens. And what it's illustrating here is that this initial light ray heads toward the lens as if it's headed toward the focal point on the right. But when it reaches the lens, it then goes parallel. So it's sort of opposite of the focal ray for the convex lens. Again, you need to label object distance, image distance, label your image and your object. Label F and 2F if the space permits you to. You don't need to label the lens. This vertical line given here is the lens. If you want to, you can label it. The principal axis, again, is drawn for you. You can label it if you want, but that wouldn't be something I would penalize you for. And then you're going to describe your images as real or virtual, upright or inverted, enlarged, smaller, or true size. Use your lens equation to solve for the image distance and then calculate your percent error. So as I mentioned, all of these are going to be basically the same. The difference is where that image is going to be formed. So I am going to mark focal and 3 times the focal on each side of the lens if I have enough room to do so. Here it tells me object distance greater than 2F, so I am going to measure 7 centimeters from my lens. And that is where I'm going to place my object, a 1 centimeter arrow. And that is my object. Central ray is always the same, so I'm going to go ahead and draw that one. And it's also, for me, the most difficult to get in just the perfect place. So if I mess up, it's easier for me to erase. So I draw that one first. And I am just a little bit to the right. Honestly, I want to redraw that, but I'm going to leave it. The next ray will be the parallel ray. And really, you only need two rays to locate the image. I wanted to show you all three so that you had some experience drawing all of them. So there's parallel to the principal axis until it reaches the lens. Since this is now a diverging lens, this light ray will diverge from the lens away. And I'm going to indicate where that light appears to be diverging from using a dotted line that passes through the focal. So where these two light rays appear to cross, which seems to be right about here, so that is my image. Now I could go ahead and try to draw that focal ray. This is not my best talent here, but I will give it a shot. So light ray goes from the top of the lens, or top of the object, to the lens as if it's headed toward this focal point on the right, and then it will continue parallel to the principal axis. Trying to get a sense of where that line is. So on the right, it will be parallel to the principal axis, and then I will draw a dotted line backward. And it does indeed seem to cross right at that point. So all three light rays, my two virtual rays and my real ray, appear to cross at this point. So now I can measure my image distance. It's 2.2. So there's image distance, negative 2.2 centimeters, because it's on the same side of the lens as the object. And I'll go ahead and label my object distance, which I said was 7 centimeters. Object distance is always positive, 7 centimeters. So now I have my experimental value. I can use the lens equation, 1 over f equals 1 over dO plus 1 over di. So then 1 over di has to equal 1 over f minus 1 over dO. So 1 over di equals 1 over negative 3 minus 1 over 7. When I plug that into my calculator, so 1 over negative 3 minus 1 over 7 gives me negative 0.47, but that's equal to 1 over di. So I'm going to write that 0.476. So that means di has to be equal to the inverse of that. So I'm just going to, and I get negative 2.1 centimeters. My measured value was negative 2.2. So calculate percent error. My measured distance, negative 2.2 centimeters, minus my calculated, which is negative 2.1 centimeters. I'm going to divide that by my calculated value of negative 2.1 centimeters and multiply by 100, and that's going to be my percent error. So negative 2.2 minus negative 2.1 divided by negative 2.1 times 100, and I get a percent error of 4.76%, which is definitely within the 10% error. The other ray diagrams on page 125 that you will be doing for homework for Monday are done the exact same way. You're just going to place your objects in the specified location, and your images will end up in slightly different locations. So just to recap, concave lenses are diverging lenses because the light rays that are parallel to the principal axis diverge from the focal point on the left side of the lens. So this focal length is considered negative. So these are called negative lenses or diverging lenses. The sign conventions, a focal point will be negative. Concave lenses will always produce virtual images. I have some examples of the rays. This is the focal ray. And this chart may be helpful in describing each type of how to draw each type of ray for the two different lenses. Here are some examples of convex and concave lenses producing real and virtual images. And this chart lists out all of the possibilities. Here's our lens equation. This is a chart of all of the sign conventions. So, rules for signs when dealing with convex and concave lenses. So I hope you found this helpful, and see you soon.